I'll record. Great. So until now, we arrived to the situation where the input varies and VGS varies with the input, which in return results in varying switch resistance. And we thought of a solution to it. And if we said that if VGS by somehow we were able to make it independent of the input, then our switch resistance will be independent of the input itself, and it will result in the linear operation, which is what we are looking for. So what we said that instead of having VDD over here, let's have a constant voltage VBAT along with the input component. So we said that let's have VBAT plus Vin plus VCM in the track phase, and in the hold phase we are having ground because we want our switch to be off. So in this track phase we want this voltage, and in this hold phase we want ground. So uh, then we said that the most straightforward way of implementing this VBAT plus Vin plus VCM is basically we have VCM plus Vin already as an input, right? So if we in series we add a battery, let's say, so and ideally we give it to the gate, then at the gate we can have this voltage where the VBAT is only needed in track phase. So we need only in the track phase of the clock cycle, which is phi or phi 1. Let's say the track phase is phi 1 and the hold phase is phi 2. So we need it only in phi 1, and there is no current drawn from this battery, as we know that there is no current passing through the gate because the gate of the MOSFET provides infinite resistance. So this we know from the concepts of MOSFETs. So this will be in track phase. So this configuration we want in track phase, and in hold phase we want a ground. So one way of keeping VGS constant or independent of Vin is to add a component to the gate voltage, which basically has a V in itself. So how do we implement a battery? So we said, yeah, we will get a battery, but then how do we get a battery within itself? Like, how should we put a battery? So the battery is required only in track phase. So let's say phi 1, right? And the current flowing out from the battery is zero. So realizing a battery with a given required voltage, let's say VBAT, is to basically realizing a capacitor. So it's basically charging a capacitor up to the voltage VBAT, and as long as we don't draw any current from the capacitor, it is acting as same as a VBAT source of a battery. So then during phi 1 or during track phase, we change the we charge the capacitor up to Vn. So this track phase, we charge this capacitor, let's say like to get a battery over here, we charge the capacitor up to the input voltage Vn, and during the hold phase, we ground the gate, right? So we need two phases, and the capacitor is not required in phase 2. Uh, so we charge it to VBAT, which is equals to VDD as of now. So then we can realize such kind of a situation. Now, in the phase 1 or in tracking phase, we have our input and we need a capacitor which will charge, right? Which will charge and act as a battery, right? So it will charge. So this is how we will get. So what is happening over here? So this is phi 1, and during phi 1, we are we are putting the VCM plus Vn into the capacitor, and it is already charged with VDD. So how is it charged with VDD already? So this is a track phase. So when it is in hold phase, so uh, in hold phase, it is connected to ground like this, and here we have our VDD, and the gate in hold phase or phi 2 is connected to ground. So the capacitor is being charged with VDD. So when we are in hold phase, the capacitor has the voltage of VDD. Now when we go to track phase, so the track phase is here. So now that's how we put at the gate the voltage VDD as battery from capacitor plus VCM plus Vin, because that's what we wanted over here. We wanted V bat plus VCM plus Vin, and our V bat is nothing but our VDD. So yeah, V bat is nothing but VDD. So that's how we implement our sample, and that's how we implement sampling phases phi 1 and phi 2 at the gate of this MOSFET in order to turn it on and turn it off. So the question arises that do we need to charge this capacitor every cycle? So in every hold, so basically in phase 2, or let's say phi 2, or in hold phase, we charge this capacitor to VDD, right? So in every cycle, do we need to charge it, or we can leave it, charge it once and leave it for all, because anyway there is no current going from this capacitor, right? So if you guys are aware about the MOSFET physics, or let's say MOSFET characteristics, so there also exist parasitic capacitances, right? So as of now, we have said that there is no current flowing, like when we have a track phase, so there is no current flowing. So if there is no current flowing, then the voltage from CB will not be reduced, right? So then we can leave, like we can charge it once and leave it for all, like we leave it for all cycles. So can we do that? Like, what do you guys think? Any opinion? Do you guys have any opinion on this? Well, the thing is, this MOSFET, even though we say that it will not draw any current, but I like in reality, when we go to lower and lower NMOS processes, so when we go to 25 nanometer CMOS process, for example, or even below that, so there do exist a little amount of current through the gate, and also these MOSFET will consist parasitic capacitances, and when there will be parasitic capacitances, which will be obviously very less than CB, but they will draw some kind of current, and there will also be a leakage current. So some amount of current will be leaked from CB. So we need to charge it in every cycle. And anyway, during hold phase, CB is sitting idle. So why not charge it in every cycle? So that's why in every phi 2, we connect CB across ground and VDD, and that's how it is being charged in every hold phase with value or voltage VDD. So let's say like basically all switches have leakage current, and we also have gate leakage. So we have as I discussed earlier, we have MOSFET parasitics, and also we change the potential at the gate every cycle. So the potential over here at the gate is changed every cycle, so it goes from VDD to 0 to VDD to 0. So that also contributes to leakage in current. So the charge also changes, and that like varying charge, it basically comes uh, from this plate of this capacitor. So hence we need to refresh this capacitor CB in every hold phase or phi 2 of every cycle. So then we have such a structure, and at this point we have VCM plus Vin plus VDD, and we have uh, this phase phi 1, and we have this phase where it is connected to phi 2, and this capacitor is connected to ground through VDD. So this is our phi 2 where the capacitor is refreshing, and our gate is connected to 0, because that's what we want in phi 2 in hold phase. And in track phase we have Vin plus Vbat. So That's the voltage at the gate. So if we charge with the parasitic capacitances with node gate, so this node to this gate, so basically we are talking about this node. So this is the gate node, and if we charge the parasitic capacitance which is existing over here, and the source is so higher, then the amount of charge from top plate of CB, as I discussed earlier, this plate of CB will have to go to supply that charge, because there do exist parasitic capacitances, as I discussed. So that will draw some current. So that will be provided by the top plate. So the voltage across CB will reduce a little. But however, the MOSFET is basically much smaller than CB. So the parasitic charge at this node will also be really small. Also, we choose CB to be like when we choose CB to be very small, then only this kind of problems will occur. But usually CB is chosen to be of very bigger amount. So these uh, abnormalities usually don't occur. So basically what we talked about is, so in track phase or phi 1, VGS remains constant by applying this kind of circuit, and due to VGS remaining constant, which is equal to basically VDD, then we can and yes, we have not considered the effect of BT over here. We have assumed it as a constant. Then when we have now we have our VGS independent of input voltage, so our switch resistance remains constant at a value of 1 upon mu n Cox omega width by length times VGS minus VT, and now our VGS is a constant value which is VDD. So this kind of a structure is basically called as bootstrapped sampling. So now the question is, how do we implement these kind of switches? Because we had this one switch, and we faced so much of non-idealities while implementing this switch. So now we had one switch, and we were struggling with it so much. So when we have now this much of switches, so what do you guys think? Is it more complicated, or it's simple now? So we can like for
We
this
can
switch,
for this switch.
I think there is an echo. Someone has left their mic on. Yeah, now it's not. Perfect. So while implementing this switch, the non-ideality was coming due to the variance of the source terminal from this switch. But when we talk about these switches, so these are somewhat simpler to implement. We'll see that how. So now coming to implement these kind of switches. So when we had to implement this switch, so we said that we will take a NMOS, right? So we were using a NMOS over here. So basically, if we want to have a switch which we want to turn on during any phase, let's say phase 1 or phi 1, or we want to turn it off when we have phi 2. So we have at least three options of implementing such switch. So what do we have? So we have NMOS, we have PMOS, and we have combination of both, which is a transition switch. So in different cases, accordingly we will use this kind of switches. So where do we use NMOS? So this NMOS is basically the gate of this NMOS is clocked by a phase which is phi. So the gate basically is clocked either with a tracking phase or a hold phase, right? So similarly, this is our NMOS, and the gate is basically clocked with phi. When we have PMOS, then the gate of this PMOS is basically clocked with pi bar. So pi bar is inverse of clock. So let's say if the phase is 1, so this is clocked with 0, or let's say the phase is 0, then this is clocked with 1. So basically that's the working of PMOS and NMOS. So when we have let's talk about the MOSFET. So let's talk about the NMOS case. So in case of a MOSFET, we have voltages, let's say Vx and Vy at two terminals of a MOSFET, and this is our gate. So when we try to equalize these two terminals, then in when there is a case where these Vx and Vy are very low, or they are basically close to ground, or they are grounded, then when we try to equal the Vy to Vx, then in this case, using an NMOS is preferred. But when both voltages Vx and Vy are close to VDD, so highest voltage, so then using a PMOS as a switch makes sense over here instead of NMOS. But when we have cases where the voltages vary, like all the way from low to high, so from low to high, we use a transmission switch like this. So the best case is our input. So our input is varying from low to high. So in this case, when we want to implement this switch, then we go for a transmission switch. So then now talking about um, implementing these kind of switches, so I'll give you an example. So we have this switch. So when we have to implement this switch, so again we have to implement a MOSFET. So we have this side of terminal and we have this side of terminal. So this is ground, right? So basically, we like, as we discussed over here, if Vx and Vy are very low or close to ground, then we the choice of MOSFET is basically NMOS over here. So we will implement NMOS over here, and the gate of the NMOS is given, like, provided to phi. So then we say that we are using NMOS over here. So then can you guys tell me that which configuration will be used over here for this switch? Either so we have these three options. So which will be used? Can you guys, like, please tell me? Because this and these two are the terminals for that MOSFET, right? So it will go like this, and this is ground. So which will we use, NMOS or a PMOS? Any answers?
A
Maybe we
combination
can
of both.
use.
Yeah.
A CMOS.
Come again.
A MOSFET is used.
Yeah, but which one?
Electrical
NMOS, like we discussed, if we want NMOS, like, see, if these terminals are terminated with voltage which is very low or close to ground, then we use a NMOS. If they are terminated with voltages which are tending towards VDD, or they are VDD, then we are using a PMOS. And if our input is varying right from ground to VDD, then we will use this transition. So now over here, this is ground, and this terminal will either go to ground. Basically we have our phases for this switch, right? So it's
You're using
ground,
an
not
NMOS.
VDD. So it will be a NMOS right over here. So over here we will use a NMOS. Over here we will use a NMOS. When we talk about this, so the terminal, this terminal is exposed by VDD, because the voltage is not even VDD, it's coming from CB, and CB is charged to either VDD or VDD plus VCM plus VN. So this switch will be made using a PMOS, because the voltage is terminated to a positive, or VDD. So then when we try to implement, so we have NMOS over here, and in NMOS, if we have phi as our cycle, so at gate we have phi. In PMOS, if we have phase phi as our cycle, then we at the gate we put phi bar. So we have, like, for this phase, like, this was the implementation, right? And when we talked about this phase, so this was phi 2. In phi 2, our gate was terminated with ground, and our capacitor, ideally we wanted to charge this capacitor, so it goes from VDD to phi 2. So while implementing this switch while phi 2, so we have the phase, or we have the cycle, which is resembling phi 2, and we have an NMOS. So then the gate will be provided with phi 2. Similarly, here also the gate will be provided with phi 2, and here we are using PMOS, not NMOS. So when we are using PMOS, so and the cycle is phi 1, so we'll provide the gate with phi 1 bar, because we are using a PMOS. So and when we are using a PMOS, the MOSFET physics says that the body of a MOSFET, so if we are using an NMOS, then we will connect the body to lowest possible, which is ground. So the bodies will be directly connected to the ground, so that it's not an issue over here. But over here, when we have a PMOS, then the body should be connected to the highest possible voltage. So the highest possible voltage over here is VDD plus Vin. So that's the highest possible voltage for this circuit. So we connect this body to this terminal, and luckily this highest possible voltage only occurs there at this terminal. So this switch is also a very straightforward implementation. But now when we talk about the last switch while implementing this switch, so the main complexity or complications arrive at this switch, because now we have VDD over here, and we have VDD plus Vin. So like straightforward, we can say that our terminals are tending towards or close to VDD. So actually they are VDD. So a PMOS, implementing a PMOS makes sense over here, right? So we'll say that the straightforward way is implementing a PMOS. So then let's say we have a PMOS. So if we have a PMOS and the phase we required is phi 2. So due to PMOS, we will provide it phi 2 bar at its gate. So until here, we are sorted. But where do we attach the body terminal of this PMOS? So basically, the body terminal in case of a PMOS is, as we said, always connected to highest possible voltage, right? So what is the highest possible voltage this MOSFET will see? VDD or VDD plus Vin. So basically it's a bit obvious. It seems a bit obvious, right? We'll go for VDD plus Vin. So should we connect it to VDD? So let's say if we connect it to VDD, then what happens? So when the switch is supposed to be in an off state, so its terminal voltages would look like this. So when we want our switch to be off, so its gate terminal will be imposed by VDD. So like if you guys are aware about the MOSFET physics, then this is a PMOS. So to turn it off, we have VDD at gate, and we know that at this terminal we have VDD. At this terminal we have VDD plus Vin. So what happens is this configuration is looking like this, and unfortunately this configuration looks like a transistor operating in saturated region with a gate to source voltage VSG. So basically source to gate voltage VSG as Vin. Basically VSG is Vin plus VDD minus VDD. We are having VSG as Vin. So it looks like it is operating in a saturation region, and in a saturation region, we have current flowing through this MOSFET. But ideally, we expected that there should not be a current because it's in a off condition, right? So this MOSFET should have been in a off condition. But ideally, if we try to implement it in this way, then we um, come to this situation where the current is flowing. So this is the complication while implementing this kind of a switch. So I want you guys to rethink that what can we do according to these three options we have, and we will discuss how do we actually implement this complicated switch over here in next video. So I think that's all for this video, and thank you so much. So if you guys have any doubts, Please do ask me.